Okay, for today's class activities, we're going to cover Chapter 27, Sections 4 through 5. Please go read those in detail and study the concepts well so you can apply them to these exercises. So we're going to go over concept questions 7, 8, and 11, then exercises 27, 37, and 68. Take a look at those and come back to the video. Okay, for concept question 7, we have an arrangement where we have a battery hooked up across one bulb. Okay, that's going to be my picture for a bulb. Okay, just to ease in the drawing. We have this delta V battery. Okay, this bulb will have some amount of resistance, and the question is, what is the current, or how bright does this bulb appear compared to an arrangement that looks like this, where we have the same battery and it goes through one bulb and then through another. So we have two bulbs and they're all identical, so they all have the same resistance and the battery is identical. Okay. So compare the brightness of these three bulbs. All right, now the relationship that connects these is through Ohm's law and through current. So Ohm's law says there will be a current, I'm going to call that I naught, through this resistor based on delta V equals IR, or I equals delta V divided by R. So if all the resistances are the same and the two voltage batteries are the same, we just need to ask, well, how does the current compare in these two circuits? All right, so in this case, this battery applies a voltage across this resistor. So the voltage across that resistor is the voltage of the battery. So we'll say that's dVB equals I naught R. All right. Now what about over here? This battery voltage is across two resistors, and they're in series. And so from here to here is dVB, but not from here to here. Now since they're identical, I can say that from here to here is equal to from here to here, only because these are identical bulbs, and they must add up to be dVB. So when I'm looking at this bulb alone, I can say that dV for this bulb, I'll call it 1. So dV1 is going to be equal to I1R, and this one, I have dV2 is equal to I2R. And together, I have dVB equals dV1 plus dV2. All right. Now, I know a couple things here. First of all, by symmetry, the voltages should be the same, which means they both must equal 1/2 dV of the battery, delta V of the battery. I also know another thing is that the currents must be the same, because whatever current flows in here comes out of here and it flows into here. So the current is the same via charge conservation. Okay, so if that's true, if these currents are the same and the voltage across one of them is half the voltage across the battery, that means these currents must be equal to half the current across this one. This current is the full battery voltage over R. So I have I naught equals dV battery over R. And in this case, we have I1, which equals I2, equals 1/2 delta V battery over R. So the currents flowing through these two batteries are equal, but half as big as the current flowing through this one. And current is really the measure of brightness. The more current flowing through someone, the brighter it's going to be, if the resistors are all identical. Okay, so that's how we can compare these. All right, now think of that same logic. Think about potentials, Ohm's law, current, resistance for number 8. Okay, so here it is. We've got the same battery. Apologize, I made it kind of squat, but these are the same batteries, so applying the same potential. In this case, we have identical resistors again, but now over here, these resistors are in parallel, or in other words, the potential across this one, which I can measure across the battery, is the same as the potential across this one. Okay, I can get from this side over to this side without crossing any other element, and I can get from this side to this side without crossing any other element. So they're at the same potential. So that means that delta VB equals delta V1 plus delta V2, if we call this number 1 and 2. So they all have the same potentials. They all have the same resistance, which means, by Ohm's law, the currents should be the same. So these have the same currents, and therefore their brightnesses are the same. Now, when I say the currents here, I'm talking about the current flowing through 1, current flowing through 2, versus the current flowing through here. In this case, since this is just one loop, the current flowing through the resistor must be the same as the current flowing through the battery because there's no other place for it to go. But over here, the current flowing through the battery supplies the current flowing to each of these. And if these currents are the same, that means in this case, this battery has twice the current flowing through it as in this case. Because the current here is equal to the current here, which is equal to the current here. So there's twice as much current flowing through this battery. It's delivered in half to this one and this one. So these are all equally bright, but this battery is going to be drained faster than this battery. Okay, now number 11. Okay, number 11. Go apply principles and think about number 11. Okay, the idea here is that resistance equals rho L over A. Okay. Resistance grows with the length of the resistor, it grows with the resistivity of the resistor, and it gets smaller with the cross-sectional area of the resistor. Okay, in this case, our resistors are all round, and so it's going to be pi r squared. So if we use L and R for our references, as the problem does state, we call this A, then we can compare everything else to that. So go ahead and look at RB. What is RB in terms of these parameters? So if you look at RB, the only thing that's different is that the radius is twice as big. But since it's squared, we have a factor of 4 increase down here. And that's in the denominator, so we get an overall 1/4. So we get a 1/4 RA. What about RC? Okay. If you look at RC, we have the doubling of the radius, giving us a 1/4 value, but we also have a doubling of the length. The length comes in linearly, so we have a 2 in the top and a 4 in the denominator. So 2 up top, 4 in the denominator, giving us an overall 1/2. Okay, go look at RD. So RD has double the length, but the same radius. So that's just going to give us a 2 up top. So that's twice the resistance of A. And lastly, our E. It's 4 times the length and twice the radius, which means squaring that 2 down here, get a 4 down below, a 4 up top, and so it's got the same resistance as A. So this is just being careful to understand the proportionality of resistance, proportional to length, and inversely proportional to area, or inversely proportional to the square of the radius of the cylindrical wire or resistor. Okay, let's go ahead and take a look at number 27. So for 27, we're trying to find the resistance of a gold wire that is 2 meters long and has a 0.2 millimeter diameter, or is 0.2 millimeters in diameter, or it has a radius of 0.1 millimeters. Okay, so this is a plug and chug, but there is some good ideas here. Rho L over A. First thing to look is that we're dealing with gold. And rho is a material property. And so I can go look in the table and find that rho for gold is 2.4 times 10 to the negative 8. Okay, and that's got units of ohm meters. Okay, Now the length is 2 meters, and the area would be pi r squared, or pi 0.0001 meters, because the radius is 0.1 millimeters squared. So if we plug that in, we get a resistance of 1.5 ohms, which a gold wire has a very small resistance. Good conductors, most metals are good conductors, and they have very small resistance. So even though it's a 2-meter long wire, it's got a fairly small resistance. Now, it's a little bit bigger than some other things we'll see because it's such a narrow diameter. The 0.1 millimeter radius is a pretty small wire, and so that smaller cross-sectional area does increase the resistance, but this seems reasonable. So let's compare that to a carbon resistor. So it's the same idea, only now we look up the resistivity for carbon, and go ahead and do that, and then plug in the numbers and see what you get compared to this one. Okay, so if you plug it in, the resistivity for carbon is much bigger, 3.5 times 10 to the negative 5. That is about 1,000 times bigger than gold. So carbon is not a very good conductor. It's because of its high or low resistivity. Okay, I'm sorry, it's high resistivity. Okay, so with this much higher resistive material, even a short piece, so just a 10 centimeter long wire, okay, that's fairly large, a millimeter square. Okay, so it's a millimeter square, so that's a decently large wire. And if you plug in those numbers, you get 3.5 ohms, okay, which is about the same size, about twice as big-ish than this one. But this one was 2 meters long and very small diameter. This one's short and a bigger diameter, but the big difference here is that we have a resistivity that's much bigger than for gold. So carbon is often used for resistors. Gold is not used for resistors because it has a poor resistivity. Okay, let's move on to 37. So for 37, we again are trying to find the resistance. This is a cool problem because this resistance is for, just a moment, my kids are coming in, they need a reminder. Hey kids, quiet, I'm recording. Okay, so 37, we have the resistivity. We look up the resistivity, so we're doing R equals rho L over A, just like before. And for copper, resistivity is 1.7 times 10 to the negative 8, which is a pretty small value. It's even smaller than gold. And copper is what we mostly use in house wires because it has such a small resistivity, and it's not nearly as expensive as gold is, and so it becomes a good material. And so even over a long distance in a house, so 20 meters, and wires we try to make the wires as thick as possible. The thicker, the more current can flow. And so we have, in this case, we have a 1 millimeter radius or 2 millimeter diameter wires, about the size of the gauge wire in a house. So that's 0.001. Okay. Plugging all that in, we get a resistance of 0.108 ohms, which is pretty small, or decently small. And then the question is, well, what is the potential drop across that wire? Now, this becomes a really important issue in wiring houses, or you're transporting electricity across large distances. Because the resistance grows with length, we need to do things to try and minimize the potential difference drop. Because most appliances, most things we use, depend on a certain voltage. And let's calculate this voltage drop across this wire. So at the breaker box where it comes to the house, it's 120 volts. And so what would it be when it finally gets to the plug or the appliance that's across at the other end of this 20 meter wire? So that's going to be by Ohm's law. We're told that the current is 8 amps. And then we have this 108 ohm wire. And so when you plug that in, we get 0.87 volts, which compared to the 120 volts at the breaker, it's not much different. That's probably actually within fluctuations. And so a wire of that diameter can be that long and still provide all the voltage that you would need for your appliance. Now, 8 amps is actually quite a large current, and so you wouldn't want that much current flowing. The bigger the current, the bigger the drop. And if you have something really large, like let's say a hot tub, you have a hot tub that draws a lot of voltage because of the heating element, or a lot of current, then the voltage drop, especially if you have it somewhere outside, a distance from your house, it could become problematic. And that's why most things that have draw a lot of current actually have even bigger wires, like really thick wires, upwards 3-4 millimeter diameter wires, still made out of copper because it's the most useful material there. Okay, last problem is going to be number 68. We're going to do it here. Okay, so go look at this problem and see what you can do. Okay, so if you look at this problem, we have this resistor here connected across just one battery. And then we have this unknown resistor, this resistor with an unknown resistance, connected across two batteries in series. Okay, and the question is, what is the resistance of this resistor if the currents flowing through them are the same? So we have these currents and they're the same. So apply Ohm's law to this problem, see if you can answer that question. Okay, the idea is that if we look at the right one, we have our voltage is V, and that's going to be equal to IR. And then across this one, the only difference is that we have 2V. So we have 2V equals I, and I'm going to put R1 for, this is what we're looking for. Okay, we're told the currents are the same. So let's just divide these and divide out those, and we've got 1/2 equaling R over R1. And if we cross multiply, we end up with R1 equals 2R. So double the voltage must be across double the resistance to have the same current. This is applied Ohm's law and resistance and resistivity.